This is Basic Optical Concepts, Unit 5, Problem Demonstrations. First, we want to look at, this is optical crosses, and what an optical cross is simply the picture representation of the powers on a lens. If we have here a lens that we're looking at from the front side, we could draw this optical cross to represent the powers being 90 degrees apart. With an optical cross, we typically just look at the cross itself without looking at the lens structure. It's just easier than us drawing the lens. And we could actually make these lines curved if we wanted to represent the curve of the power. But again, we don't need to do that. So powers on lenses are always 90 degrees apart, and they're referenced from 0 starting on the right, 90's at the top, and 180 degrees is on the left as you look at the front of a lens. This is considered the entire 90-degree line, even though this would be the 180 plus 90 would be in a circle 270 degrees, and this in fact would be equal to 360 degrees. We just don't specify those degrees because it's redundant. It's representing the same line on the lens. So if I wanted to represent a spherical lens drawn on an optical cross, and here we're talking about the total power of a lens, we would simply choose any two meridians that are 90 degrees apart from one another and put them on the optical cross. So let's just pick, for the fun of it, we'll take two that are different than 90 and 180, and let's say this is 45. And this is 135, and we have a -2 spherical lens. Then we would label this -2 and this -2, because that lens has the same power in all meridians. I could also draw that a different way. Instead of drawing it at 45 and 135, I could write my -2 right here and my -2 right here. The fact that these are both the same power indicates to me that that lens is a spherical lens. If I wanted to represent a cylindrical formula on the optical cross, again, I usually start with my 90 and 180. And let's say we're given a lens that has -2, -1, axis 10 degrees. The first step that I would tell you to do is to transpose that lens formula to make placing those powers on an optical cross a little bit easier. Transposing means that you algebraically add the sphere and the cylinder together, and that gives you the new sphere power. So -2 plus a -1 is -3. Same sign just means a bigger number of that same sign. Change the sign of the cylinder power from minus to plus, maintain the value here, and then change the axis by 90 degrees. Since this is less than 90 or less, we just add 90 to that, so it'll make that 100. So now what we have, our sphere power is always represented on the optical cross on the axis. So we have -2 is on the axis of 10 degrees, and we have -3 to be on the axis of 100 degrees. So on our optical cross, we can draw this now. 0 being here, 10 should be right about there, and 100 be over here. -2 is found at 10, and -3 is found at 100. Notice that this power of -1 or +1 is never represented on that optical cross. This is the amount of cylinder or the amount of astigmatism this patient has, but the cylindrical component of that lens And that's simply the distance traveled between these two powers. Between a -2 and a -3 is 1 diopter. Between a -3 and a -2 is 1 diopter. Distance traveled on a number line between those two. So this 1 diopter difference should be represented right here as the distance between the two powers on a lens. If you're familiar with doing lensometry already, these are the numbers that you'll read in a manual lensometer. You'll read a -2 power and you'll read a -3, and you have to calculate the amount of astigmatism or cylinder that that lens has. Basic Optical Concepts, Unit 5 demonstrations continued. Here we have 2 lens formulas, and our assignment is to put those lens formulas onto an optical cross. They represent the total power of a lens. Again, the first step I would tell you is to transpose the formula into the opposite. Here we were given a lens formula in plus cylinder, and let's transpose it to minus. So we algebraically add the sphere and the cylinder. Here we have unlike signs, so we subtract and maintain the sign of the larger. But when I subtract these two, -2 and a +2, I end up with 0, or in optics we call that plano. Change the sign to a minus, maintain the value, and change the axis by 90. And since we have 180 here, we subtract 90. Again, now that'll tell us that the -2 is at 180 and the 0 or plano is at 90. So we can simply fill this in. Helpful if we put the right one on the right meridian. Notice here now the distance traveled between 0 and -2 on a number line is 2 diopter units, and that should correspond with your amount of cylinder in that lens. So we have a power of plano at 90 and -2 at 180 on that lens. In this lens formula, again, we would transpose this, a plus 150 and a -2, we subtract and maintain the sign of the larger, and so we end up having a -1/2 +2, axis 45. So now we can put 150 belongs at 135, and we have to draw 135 in here, and that's split right between those two. And then 45 will be at a 90-degree angle to 135. And we can put the plus 150 at 135 and the minus 50 at 45. The distance traveled between these two, we're going from minus 50, somewhere in here is going to be 0, and then from 0 to 150, so we are traveling at 2 diopter units here once again, and that corresponds to the 2 diopter units in the cylindrical value. Basic Optical Concepts, Unit 5, demonstrations continue. In the previous demonstrations, we were looking at the total power of a lens and representing that on an optical cross. And essentially that is what's represented here, the total power of this lens. We can actually break this lens down into the front surface, because it has a diopter power, curvature, and the back surface, because it has curvature as well. And in this case, we're actually given the front surface power and the back surface power, and we're going to use an equation that says the front surface plus the back surface equals the total power of the lens. So we will use that information then to add this plus this will equal a new power at 40, and F1 at 130, F2 at 130 is going to give us a new power at 130, and do the arithmetic on that. So plus 6 minus 650, again, subtract and maintain the sign of the larger, is a minus 50, plus 750 minus 650, subtract and maintain the sign of the larger, will be plus 1. So now we have our total power of the lens, and we can write the lens formula from that as you were working with in your other problems and your class notes. If we want to write this in minus cylinder form, we would start with the most plus meridian first. Out of these two, the plus 1 is going to be more plus because it's actually in the plus side of the number line. So we'll start with the plus 1. The sphere always tells us what our axis is, so our axis will be 130. And the distance traveled from a plus 1 to a minus 150, it's going in the negative direction on the number line, so we want to put negative there. And we went from plus 1 to 0, 0 to minus 50, be 1.5 diopters. Now so we've calculated this at 1.5 diopters. Before we go too far, let's check ourselves, because one of these surfaces should have a diopter and a half difference between the two powers. Well, this one's the same, so it's a spherical surface. Here we have a power of 6 at 40 and 750 at 130, and here's our power change of 1.5 diopters. So this needs to be represented here, which needs to be represented here. All three of those values need to be the same, or you've done some mathematical error or some error. If we want to designate this in plus cylinder, we just start at the opposite side, minus 50. That gives us our axis of 40. The distance traveled is the same regardless of which way we start, from a minus 50 or a plus 1. So that's why we can keep our unit the same. And we just change our sign because we've traveled from the minus into the positive direction on our number line. So another way of thinking about a lens formula is we have a plus 1 diopter power on this lens at 130. If I travel 1.5 units in the minus direction on our number line from that plus 1, we'll find the other power on the lens. Now, there's a couple other things we can tell about this lens, seeing all three of these surfaces. We can tell what the base curve is of the lens. Base curve is defined as the least plus on the front side. So in that case, here's our base curve. Because it's plus 6 is lesser value than plus 750. We can also tell where the cylinder was ground in the lens. Cylinder can either be placed and ground on the front side, or in most cases now today, it's actually ground on the back side. But we have some old lenses running around, and we found one here that actually the cylinder was ground on the plus side of the lens because our power changed. Here's our cylinder right here. The power is not the same on the front side, and that actually is on the plus side of the lens, so we call that lens ground in plus cylinder. We'll take another look at another lens where it was actually ground in minus cylinder in the next demonstration. Basic Optical Concepts, Unit 5, demonstrations continued. Once again, here we have front surface powers of the lens and the back surface power, and we're asked to write the optical cross for the total power, write a lens formula, determine the base curve, and the cylinder form it was ground in. So we'll start with calculating the F total. Remember, it's F1 power at 180 plus F2 power at 180. So we have unlike signs, we subtract and maintain the sign of the larger. So 6 minus 7 is 1, and 7's bigger, so it's going to be a minus 1. Plus 6 minus 850, subtract that, it's 250. This is bigger, so it's going to be a minus 250. And now we're ready to write that lens formula. And if you want to write it in minus cylinder form, you start with the most plus value, And again, you're referencing a number line, so -1 is closer to the plus side of the number line than -250. So we would call the -1 the most plus value. So we start with -1. That will generate your axis. The distance traveled from -1 to -250, well, we're going in the negative direction, so we can put the minus sign, and we're going 1.5 units, or 1.5 diopters in this case. If I want to write it in plus cylinder form, I start with the most minus. Now I'm going from -250 to -1. I'm going in the plus direction on my number line, and I'm going the same number of units. I don't have any power change here, but I do have a power change between 7 and 850, and there I found my 1.5 diopter power change. That better match this, which matches my cylinder power. The base curve is defined as the least plus on the front side of the lens. Well, I have the same power here. Base curve is just going to equal that power plus 6 diopters. And whether that lens was ground in plus cylinder or minus cylinder form, I have to look at the front side of the lens and the back side of the lens. This is a spherical lens here, a spherical side of the lens. It has no power change. So it wasn't ground in plus cylinder. My cylinder is located here, and I've actually identified that before with that 1.5 diopters. So it's ground on the minus side, so this was ground in minus cylinder form. And ground in and written in are two different concepts. Ground in is where they actually place the cylinder excuse me, during the manufacturing process, and we can write it in either form at our whim or whatever the office requires.